So thank you very much for your hard work. I see you're very applied. But because there's not much time, if you agree, I can sort of scroll through the solution and then allow you to finish yourselves, convince yourselves to the end. Is that okay for you?
Make a few comments.
Or make a few comments, questions, something like that. But sort of like an assisted finish of the exercise. Is that okay? Maybe some of you prefer to completely do it on by yourselves, but but okay, the plan is just to do that maybe for like 10 minutes, just quick, more like getting view. And then I want to switch to a different thing, go back to these chains and show you some interactive plots of the chains. Okay, so this is just a bit quick, and then it's mostly if you have comments or questions. So this was part A. It was just the standard. This was the main thing. So maybe I can do this thing. This was the main point to write out, to imagine that your matrix is some 2 by 2 matrix, the VDG matrix, and then multiply it all out, and then do a matching of the Hamiltonian you have with this, and then you read out the PQRS. That's it. So you probably did it that way, and you need to commute, anti-commute the CSH. I think probably everyone did that part. So you probably did everyone arrive at that matrix there? Yes, I imagine yes. Okay. Then it was identifying this D vector. Okay, so it's just a 2 by 2 matrix. So the D vector in the end should look like that. These are off diagonal sigma x, sigma y, and then on the sigma z is the normal dispersion. And then the band structure is just the length of the D vector. That's a useful trick. It's just the square root of the squares of the coefficients of sigma x, sigma y, sigma z. Okay. So you should have that dispersion. This is the standard superconductor dispersion. Also, Pascal showed it in lecture today. Okay. So now, where are the gap closing points? That's now part C of the problem. So you need to make it 0. You do it by making the first term 0 because it's squared, and the second term 0 because it's squared, and it's a sum. So they both need to go to 0, independent. I mean, at the same K. Okay, so first you look at the zeros of the normal dispersion. That's 1, and the zeros of the gap. That's 2. So the normal dispersion, where does it go to 0? Well, if your chemical potential is outside the bands, there's no solution. There's no Fermi surface, so this dispersion is never 0. But then inside the band, of course, it goes to 0 at what we would call the Fermi surface, right? It's the collection of K points at which the dispersion goes to 0. Then special points are exactly mu equal to 10 times the potential second axis. Social and it can get meant that there are many points. The Fermi surface really aren't just being kept. So, like, imagine a Fermi surface around the gamma point. As I'm lowering the chemical potential, it shrinks down to just being the gamma point, and then the chemical potential. Okay, so that's easy. And then for the pairing, now it's different for the P wave and the D wave, because the P wave is odd. This is odd in K. So it will go to 0 at all the momenta which are even in K. So any momentum and minus momentum is the same. That's a time reversal invariant momentum, if that's the case. Sorry, those are the 4 points, gamma, x, y, and m. Gamma, x, y, and m. These 4 points, when I take the negative of them, I come back to the same point. So these are even. Then the dispersion is odd. It has to go to 0 there. And it turns out it doesn't go to 0 anywhere else. So you can just solve these sine functions, and that's the possibility. The D wave dispersion is even in K. So it's not forced to go to 0 on all these points. you can solve it, and you should obtain that it goes to 0 at the gamma point and the m point. Because it's the points where the cosine is 0. I mean, both cosines are 0 at the same time. Okay, easy peasy. So now we combine all that, and we see that either when the chemical potential is finely tuned, the Fermi surface collapses to the gamma or m point, then it can meet also where the pairing is also 0. And that's how you obtain. Okay, so I'm getting into too many details. I should go faster. The point is, you obtain. What did you do now? Wait, something is wrong. I'm sorry about this. I'm not seeing why did we get this. Just one moment. Yeah, somehow it's not showing me this part. Okay, so this is what you should obtain. The P wave has 1, 2, 3 gap closing points, and the D wave only 1 and 2. Then the Fermi surface is at the gamma and m, but this guy also closes the gap when the Fermi surface collapses to the x and y point. Okay, and now comes this tedious calculation. No need to show you the details. The G vector we have already shown, and now you have to plug in into these formulas that we gave you. So, well, I'm not going to show much of that. Just to tell you that, for example, if I plug in this D vector into this big sausage, I work it out the sausage, and it's this, and I'm only caring about the sign of that sausage. Then T is strictly positive, so I can simplify a bit, and this is really what I care about. I really care about the sign of the cosine of ky for these special points. What are the special points? The special points are those where this D vector is somewhere on the x-axis, as explained in the exercise. Okay, so this is now 3 equations I need to solve. 1, 2, 3, because it's a vector equation for x, y, z component. And I need to find these special points kn. Once I know them, I can calculate the sign of this, and that's going to give me the channels. Okay, and then this is the only tricky part, that this equation, the third one, if you look at it, is just the Fermi surface. This is, by our definition, literally, epsilon k minus mu equals 0. So that it just tells you the special point needs to be on the Fermi surface. And then additionally, the sign needs to be like that. So this is the graphical solution. You say, well, if I need to sit on the Fermi surface and the ky, the sign of ky needs to be 0. So I'm either on the line ky 0 or ky pi. So I'm on the purple line and I'm on the Fermi surface. So that's the intersection. That solves both equations here. Okay. And then if the chemical potential is bigger, the Fermi surface goes at. So I give you that in the figure. The Fermi surface changes shape. It goes here. Then the intersection happens on the ky equals pi. So that's a difference. Depending on the chemical potential, either the is there or there. And okay, then you have these solutions. Either the special case at some finite x value and ky value 0, or it's at some kf in the x direction, but at pi on the ky. So these are the special solutions depending on the chemical potential. Okay, and then I can plug these special solutions back into that sign expression, and then it's either plus or minus 1, because the ky is either 0 or pi. And that's how I end up getting the Chern number. Is this logic okay with you? Yeah, okay. I think some of you got all the way to this point. And so there's not much to say. So now I do the D wave case, and it's sort of the same business. So this thing of which I need to find a sign is now a bit bigger. At least I didn't find a quick way to simplify it. But okay, the real hard work is finding the special points k, again solving 3 equations at the same time. Again, you need to look at the band structure. One equation is telling you it needs to be in this region of the Brillouin zone. The second equation is telling you it's either on the purple line here or here. And then the third equation is telling you, again, it's on the Fermi surface. So you need to draw the Fermi surface, the orange. It needs to be on all these 3 at the same time to solve 3 equations. Yes?
The procedure made sense, but intuitively it didn't make sense to me why this gives you the Chern number. So like why did you use this like kind of ray that only has one component?
Yes.
I mean, how does that tell you how
Okay.
fast it wraps around?
Okay, I take that as a signal that you're bored with this and you want to see the interpretation. Okay, so let me scroll to the end and then I'll tell you about it. Okay, so let me just say that here the difference is that sometimes you even get 2 solutions. Here, you see, because I need the green region, the orange line, and the purple line. There's actually 2 solutions. So there are 2 cases, as opposed to the P-wave case. So I'll answer your question, just let me wrap it up. And that's why then in that formula, I have 2 of the P's, not only 1, but 2 of them here. They add up. So those 2 points both contribute. And that's why the Chern number ends up being 2. That there are 2 contributing points. Okay, and then the summary, this is your final result, is this, the Chern number being 0, plus minus 1, or minus plus 1, 0, 0, minus plus 2. The plus minus sign here is the plus minus sign here. Okay, and then you're almost done. This other thing is not so important. And then the winding. This is really a simple exercise. So just plugging the expression of the delta into this integral I proposed, and then just solving that thing. So the k point, you write it in these sort of polar coordinates, and there's really nothing special about this. Maybe what can confuse you is that, for example, sine kx is sine of, and then in polar coordinates, kx is kf cosine theta. So you have sine of cosine. It seems horrible, maybe. But then you just use what I wrote, that kf is small. So imagine that the Fermi surface is shrinking because it doesn't change the topology, just bigger or smaller. So then you do a little development to lowest order in kf, right? And you solve the integral, and you'll end up with the winding the same to the Chern number, and that's it. So there's not much to say. You'll have this document. You can read it piece at home. So now let's come to the interesting question about the Chern number. So the idea is this actually works in lower dimension too. So let me first show it in 1 dimension. Can I do this? So, okay, so let's start like this. Chern number, usually, well, it's this integral of Berry curvature. There's some horrible expression you need to do, even if in a 2 by 2 problem. And who wants to solve integrals? I mean, come on, they don't pay us for that. So then sometimes there's an algebraic approach. So let's say in 2D, let's say I have a vector, I have some curve, dk. So what am I trying to say here? So it's a 1D problem. It's a 1D problem, and I have a d that's in the plane. Okay, so d is in the plane. So let me draw a reference circle around the origin, and now I have some curve like that. So that is my d vector. And now, if my question is how many times does this d wind around the origin? Let me draw another situation where the d does maybe that. Okay, and the third situation, so it's oriented, it's going in some direction always. And let's do this situation a little bit. like that. So this should give me +1. This should give me 0, and this should give me, what is this?
One as well. I mean,
Sorry,
+1 as well.
the +1. Yes, I don't care going a bit backwards and forward. So then, and then this is like a mathematical theorem. If it's a smooth curve doing that, a continuous curve, well, do I need to really solve some integral? So I could solve an integral. I could write in polar coordinates, doing complex coordinates. So I introduce x and y, and now I take d to be a complex number. So I take dx, dy, identify that with dx plus I dy. So that's some number z. So this is identification, a mapping. Then I could look at z equal amplitude of z times e to the I phi. All of these are functions of k, of course. Just like the d is a function of k, right? And then I could look at the phase, right? That this thing. And I would integrate over all the k space. I would take a derivative of this phase and then integrate it and hope and get that, right? So the phase slowly grows from 0 to 2 pi. Sorry. But why should I do this? Why should I suffer? This 5k should be complex. So that now I do this method. I just draw a ray like that out to infinity.
Okay. And you're seeing like how many times it cuts that ray?
Yes, I want to see how many times it cuts. But then also when it cuts, I need to understand, is the curve moving this way, or is it moving the other way?
About the sign.
That's why I care about the sign. So in this low dimensional example, this is also this is the tangent of the D curve. So what I do is something like D cross delta K of D. So delta K of D is that small arrow. The D is here at that point. So the cross product is going out of the plane. So then I do Z dot that. And then this is either positive or negative. And that's telling me in which sense it is winding. So that's sort of the thing. So first step is, of course, that the D covers the whole sphere. So, but when you look at this D vector, when you change kx, ky to go on the Boolean zone, it obviously does all the equators and everything. So it covers the whole sphere. But you cannot prove that the wrapping is it 0 or non-zero, because it maybe starts to cover it, then it sort of stops, come back, and maybe covers it 7 times. But then you do this ray method. And then if you cut wrongly, well, it's all fine. Because here the curve is moving to the left, here it's moving to the right, and here it's moving to the left. So when I add 3 times that thing, only the +1 will remain. So that's a lower dimensional example. And then you just did the example when it's on a sphere, and the D vector, the capital D vector, depends on a 2-dimensional momentum, and itself is 3-dimensional vector. But the logic is the same. The only thing here in wrapping, you need to understand whether the normal on the surface is out or in. And that's this expression, D dot delta kx d cross delta ky d. That's the thing that tells you whether you're cutting through the normal part of the surface or where the surface bent over itself, so the normal is opposite. That okay? Okay. No one found a mistake, so then it's correct. Okay, so let me show you this this thing with the chain. It's sort of fun. So how should I do it? I should again do fill in and just pick a different window. It's just very simple. Again, So I want to come back to this Rajba wire. You don't want? Yes, yes, of course. I need yes. Yes. Sorry. Yes, I'll just write down the Hamiltonian we are looking at. So we have a normal part, which is here minus p cosine k minus mu. That's our normal part. Okay, so ck dagger up, ck, well, sigma sigma, right? It's both spins are hopping, and then I have the S wave pairing. So I have delta S, ck up, dagger dagger, c minus k down, plus the Hermitian conjugate. Okay, but what's the fun ingredient? Sorry, magnetic field. I put sigma y, so it's in the y direction on the wire, and then the spin orbit coupling I pick to be in the z. So just for top, and then this is sine k. So you might say, wait, these are weird. Well, this is just hopping on a lattice. What I did in the lecture is k squared over 2m is just near the gamma point. And then also there, I just wrote linear k. But on a lattice, it's not linear k, it's a sine function. It needs to be odd in momentum. The spin orbit. So that's the Hamiltonian. Let's look at the Hamiltonian. The projector is, it says on. So now the nothing is visible. Probably one of you, but yes. Is it your computer? I shared it. So, can you shut the projector? Switch it off and switch it back on. Well, okay. I'll use that time to say. So you can do. Yeah, that's it. Wow. Yes, I prefer it. Okay, so this is just. Do you care about this? I can just tell you. You can you can define your Pauli matrices, and then you can define tensor products of Pauli matrices, and then your whole Hamiltonian is just one line. It's this line here, like that. It's just some tensor product of different Pauli matrices in particle, whole space, and spin space. So it's very easy. Okay, and then you have to suffer a bit more to make this kind of plot, but it's also not so bad. So what are we seeing? Let's tune it somewhere. So let's start with magnetic field 0. It's a bit slow, sorry. Let's pairing 0. Okay, so the red bands are the electron bands, and this is the spin orbit split bands that you know, and the blue are whole bands. And then we can also just click a Z and see the Z polarization. So it's only spin orbit. So the spin orbit polarizes this. This is the up, and the green is the down, right? And the holes equally. Okay, you can also look at Sx or Sy. They are 0 now. Okay, so then what did we say? We said, well, keep the chemical potential near this point, and then switch on the magnetic field. So like that, and the magnetic field will open a gap here, the magnetic field. Okay, because it will push apart the two spin directions. So let's take a look. So SZ direction. Now this used to be the purple. There was a purple band and the green bands, but now you see it's becoming black here. because here the spin is not anymore polarized, either plus Z or minus Z. It's in the plane SY where the magnetic field is. So the SZ component is 0. That's black. Sorry, I should show you the legends. Later you will see the legends, but this is a hole electron. So black is half-half, and this is the spin. One spin, the opposite spin, or 0 spin is again black. Okay. Okay, let's go. And now we just need the pairing. So let's look at again electrons and holes. Well, they are meeting here. So we hope when we turn off S-wave pairing, they can gap out. And that should. Yes. Okay, and that's it. That's how we got to a Kitaev model from a spinful model. Let me switch off the pairing again. And let me just increase a little bit the magnetic field, maybe. Like that. So it's more visible. We are just gapping out here. So this gap that opened here is now a topological gap. It's effectively a P-wave gap. Because inside is one band. Okay, so then you can check that there's a transition. There's a transition. This topological transition is happening with this criterion. The criterion is that the square root of mu squared plus delta squared equals B. Or, okay, let's do that. Okay, so we can check that if mu is 0, as it is, and let's make, if mu is 0, then just B equals delta. So let me put delta 0.5, and let me put B 0.5. Like that. So that's exactly where we were. It looks, sorry, you know, as 305 is. Oh. So now you see there is pairing. It is a superconductor, but the magnetic field is too strong. So this guy is gapless. It's at transition between two superconducting states. So here it's black, the electrons and holes are fully mixed. It's a paired state. But it's not gapped. The magnetic field is too strong. So if you look at SZ, sorry, more SY, go along the magnetic field. Yes, so the magnetic field is not achieving a good polarization at all, but it is killing the gap. Okay, so this is the transition point. So if I increase the B a little bit from this point, the gap will open. If I decrease the B a little bit from that point, the gap will again open. But these two states are different states. In one, B is larger. In the second, B is smaller. One of these is the topological superconductor. The other is a trivial. Right? I can also drive transitions by just changing the chemical potential. I could leave these other parameters fixed. Then I could slowly move into the band and eventually drive a transition. Okay, let me not do that like this on the fly. But instead, I want to just show you now some static plots that capture some physics. And I think that's perfect 5 minutes for that. Just 3 minutes actually. So here the question is, let's say you're an experimentalist and you observe this gapped system. Can you tell, is it on the topological side or on the other side? Can you tell? Let's check. So these are the static plots. So this is right at the transition, as I just showed you. So the pairing exactly equals the B, but chemical potential is at 0. And that's exactly the transition point, of course. There's nothing special. That's our initial point. And now let's move into the two phases. So let's decrease B or increase B. Look at these two. They look the same. There's really not much difference you can notice. In the electron hole part, I was going to draw you for the S epsilon, but doesn't matter. If you keep decreasing B or keep increasing B, the band structure will evolve a little bit different. Then, if you are here, you can reasonably say, well, there was obviously only one band, one electron band, that's paired with one hole band. So, this was a pairing inside one band. And you can sort of say, well, then it's a topological superconductor. While here is not obvious at all, because there's one electron band here, and the other one was here, and both of them are paired. So here I cannot apply this criteria. Okay, but the B needs to be large enough to even attempt this identification. But you can play like that. Then here I also, I'm not sure this is very valuable, but this is sort of the opposite limit, just to say that you could also do things like that. Imagine that first you crank up the B a lot. So you see one electron band and the second band, they are completely spin split. So that's the picture below. Is it? Yes. Yes. So that's the spin polarization. Look, the one is completely spin down and the other is completely spin up. That sounds like a good idea. Let's just split these bands. Then at the Fermi level, I only get one electronic band. Only the spin down, right? Okay. So that's a good step. But now, let me turn on the pairing. Okay, I turn on the pairing here. But the gap doesn't open. Because it cannot open. In this fully spin polarized band, it cannot, it's supposed to, the pairing is between up and down. It cannot pair up with up. The S-wave pairing. So if I start from an electron band that's fully polarized up, and I try to pair it with itself, with its own whole version, it cannot pair. So the gap never opens. What I need is I need to switch on some spin orbit coupling. Because the spin orbit coupling, it tilts the spins a little bit. So from the fully down polarized green, I get something that's green and a little bit yellow. So the spin orbit cants the spins a little bit. And now, these two, the electron and the hole, have some component of opposite spin. If you tilt the spin, then it's not fully up. It's a little bit down. And then they can pair. And now this is a topological gap here. But you see, this is very impracticable because the gap is tiny in this kind of situations. Well, also because, you are close to momentum pi, and both the spin orbit is odd in case, so it goes to 0 here. So the spin orbit actually needs to be cranked up a lot to be efficient here. Okay, so I thought maybe these two examples just to show you how you could play and plot and try to understand. And it's easy to add anything else. Further hopping, complicate the band structure as you wish. Try different angles. Okay, still a couple of minutes if you have any questions about either the exercise or about this. Yes.
So I didn't get to. Green and violets are SY spins in opposite directions. And actually,
yes.
to couple them, to open this gap, you need them to be tilted a little.
Yes.
These I didn't get why. Why can we just couple plus?
Okay. So we agree that for the Y, X, or Z does not make any difference. S-wave pairing up and down is singlet, so it pairs right.
Yeah.
Okay. So let's not talk about Y. Let's talk about Z. So if there's only a magnetic field, let's say it's around the Z. Okay, just because I dislike Y. but doesn't matter. So then the electron is up, but the hole is also up. And the S-wave pairing cannot pair in the same. So look, let me tilt. Let me tilt. If I tilt a little bit, the way I view it is that it is that now is decomposed as being partially up. Well, I should put it, sorry. It's I should decompose it as being along the Z, but shorter. Redraw, referee. So this was the original situation. Now, because it's tilted like that, then it's partially here, but partially it's here. Yeah, like that. And this guy get tilted oppositely because opposite momentum goes the opposite way in spin orbit, like that. So now that guy has a little projection like that. And then the singlet pairing says, look at these spins. They're opposite Ks and opposite spins. That's S-wave can pair them. So the pairing here, that's why the effective topological pairing is delta S multiplied by alpha. Because this little thing here is proportional to alpha. It's the spin orbit that tilts it. Does that make sense? Is the picture good? Tilting. But to repeat, so the purple arrows were the B, and then the orange arrow was when I turned on alpha, which is orthogonal to B. You know, so let's call this X, and let the B was the Z. You know, it's just important that they are orthogonal. Doesn't matter. Yes, you see. So that was the B, and then the spin orbit tilted them. It wants to push them into the X, but then oppositely for the opposite case. The B wants to make everyone the same. So the K and minus K have the same B, so they cannot pair. Helps? Is for others okay?